Hello class. For this video I'm going to explain rotation in a cylindrical container and the details about it, how we get the formulas to decrease the confusion for this topic. So remember we talked about different acceleration we have for the direction of r, which is the inward, and for the z, which is the gravitational acceleration. So for this topic we are going to have dp over dr. It's going to be rho times acceleration. Acceleration for r direction is going to be r omega square, and the next one was in theta, which is the if I watch the container from top view, so this is our direction and this is going to be our theta direction, so rotating. For that one we're not going to have any acceleration, so derivative of p over theta is going to be 0, and for p in z direction, which is the vertical, we are going to have a negative rho g. Okay, so these are the derivative of pressure over our main axes r, theta and z. Let's decide about main axes. So for this case I'm going to have r here at the bottom starting from the center, and for z again at the bottom and center, upward is going to be positive. So sometimes we move this z to the surface, sometimes we keep it at the bottom. Doesn't matter, it's just about which one you're convenient with it, and it's your style of selecting. So it doesn't matter where we put z. Depends on the question you have. You may feel it is easier for you to put the source or the origin for z at the surface. Okay, so then we also talked about when we have a parameter dependent on other parameters, if we want to find derivative, we are going to have apply that for both dependent parameters. So dr plus dp dz dz. So as you can see, I didn't include theta because the acceleration we considered it's going to be 0, so it is going to cross out from our equation. So let's plug the numbers we already found, because we found the derivative of p over r, this value, and for z this value. If I plug those numbers, I'm going to have rho r omega square, and for dp over dz is going to be negative rho g. Here I'm going to have dr dz, it's going to be dp. Okay, so now I'm going to consider a special case when we have dp equal 0. So when we say dp is equal 0, it means we are talking about a line or a surface which we have a constant pressure, and we call that constant pressure line or surface, and sometimes we call it isobar. Iso means one, and which means whatever property we are talking is a constant over that surface. So if I include this condition, which is dp equal 0, we are going to have dz over dr equal that ratio, which is I can write this color, or omega squared divided by g. Okay, so this is our dz over dr. And for what case? When we have constant pressure. I can write here isobar to not to forget about it. So this is going to be when we have dp equal 0. If I integrate this equation, I'm going to get this. Z for isobar is equal omega square r square divided by 2g plus a constant number. Let's call it c. And as you can see, this is going to be a formula for parabola. It's a second order with a c constant, and this c is going to show us the distance of the isobar from our origin z, which is at the base. So if I want to find or I want to investigate isobar at the surface, or just the surface of the liquid here, which we called here zs. So let me write, if I want to investigate zs, which is isobar at the surface, or the surface of the liquid, it is going to be omega square r square divided by 2g plus that constant is going to be distance from our 0, 0. What is the distance from 0, 0? As you can see here, we named that distance hc. So that distance is going to be hc. So this is just for the case of the surface. Let me write this s as for the surface. So now I'm going to extract a formula for that parabolic line. Okay, I didn't tell you this how we extract this formula, but now I can explain how we get it. So it's very easy. Basically, we calculate the volume of the parabolic volume we have inside the container, cylindrical container. So volume is going to be equal integration from 0 to maximum r, maximum distance, which you can see here, it's r, for 2 pi r times height, which is zs, height from the surface, because I want to find the whole volume, times dr. So this is going to be the volume of that geometry, the blue colored water, when we have a rotating liquid inside. And also we know that at the initial condition, when we're not rotating container, the volume is going to be pi r square times ho, which ho is the initial height when we're not rotating. So this ho is shown here. So if you integrate the first one and include v equal pi r square ho, we are going to get this formula. Where is it? This color? Zs is going to be equal the initial height minus omega squared divided by 4g times r squared minus 2r squared. So this is going to be the formula for the surface. So you can use this r, for example, if the maximum radius is, for example, 2 meters, and you want to find what is the height of the surface at, for example, 1.5 meter, you put 1.5 meter here, you have initial height, you have the maximum, which is the 2 meter diameter, radius, you have omega, you can find what is the height. For example, if r is 3 meters, 1.5 meter is going to be here, so you can get this distance, which is Zs, using this formula. So this is another formula we found. So let me identify the important formulas here. Okay. The next one, using this formula, I can get the maximum height difference. So I'm going to call that maximum height difference delta z for the surface, but max. So that is going to be basically delta z at r, which is, let me delete these, which is here. So z at r, zs at r, minus zs at 0. So here, zs at 0. So that height difference is going to be maximum. So this is delta z s max. So if I put the values here using the previous formula, the delta z max is going to be omega squared divided by 2g times r squared. So this is our maximum height difference between the surface at the center and the side. Okay, now I want to find the pressure difference between 2 points. Using this formula, I can write and find pressure difference. Instead of dP, I'm just converting and using P2 minus P1, which is same meaning. P2 minus P1 is going to be rho omega squared divided by 2 R2 minus R1 2 minus rho G Z2 minus Z1. So for this case, we don't need to have any constant number because I included 2 points. So one of those points can play that role of that constant. So this is the formula which made us a little bit confused, and we can use this as it is for our calculation when it is the topic is about 2 points. If it's about 1 point, let's see how I'm going to deal with it. I'm going to write just, okay, let me write and then we can see. P is going to equal rho omega squared divided by 2 R squared minus rho G Z, and you can see the equation right now I'm writing must be exactly like a yellow one. So I'm going to add a constant number, for example C2. This is, let's call it C1. So C2 is going to be summation of the values I'm getting from this part and this part. So those are going to be accumulated inside C2. That is why when I'm using 2 points, I don't need to have a constant number. When I'm using 1 point, I need to have that constant number. And how I can get this constant number? I need to find 1 point exactly like this, put inside that formula to get constant number. So those two equations, actually they are equivalent and they are similar, and the only difference is for the first one, the effect of constant number is applied by for example, the point number 1. For the second one, that C2 constant is going to get by another point, like a point number 1. So we can calculate that. Okay, now I finished the whole topic about how we can use the formulas, all of them, and the most important equations. So you may have, you want to find something over isobar, so you can use these equations. You want to find the surface, something about surface, you can use these. Or the maximum height difference, this equation. If you have 2 points, the yellow one. If you have 1 point, the green one, but you need to take care of that constant number.